We all know what battery degradation feels like on our phones. After a couple of years, the battery life tanks, it gets hot, charging slows down, and one day it barely lasts half as long as it used to. So I think it's natural to wonder, if lithium-ion batteries degrade like that, isn't a second-hand EV going to be basically worthless? Are we heading for 10-year-old cars with half their original range? Or a massive battery replacement bill just after you buy one? I recently bought a second-hand EV, and that's exactly what I wanted to figure out. How much do batteries actually degrade, and how can you tell if you're buying a good one? Smartphones degrade fast. EVs use similar chemistry, but the real-world data shows that EV batteries usually outlast the rest of the car. So what's going on? And more importantly, if you're buying a used EV, how do you actually measure battery health in a way that you can trust? In this video, I'm going to walk you through the exact process I went through when I was looking into battery health, what the real-world data says about degradation, what actually causes it, how expensive things can get in worst-case scenarios, and most importantly, how can you test battery health yourself before buying? I'm Rosie, an engineer with 20 years experience developing clean energy technologies and founder of Partalote Consulting, who provide advice to clean tech startups and investors. Welcome to Engineering with Rosie. It's completely normal to worry that an EV battery will degrade as fast as an old smartphone, but the reality is much more reassuring. Unlike phones, EV batteries are equipped with advanced thermal management systems like liquid cooling and built-in buffer zones that prevent them from fully charging or discharging, which significantly extends their lifespan. So how quickly do they actually lose capacity? According to a recent massive study by Geotab that analysed over 20,000 real-world EVs, the average battery loses 2.3% of its capacity per year. Another study, the Generational 2025 Battery Performance Index, looked at over 8,000 real electric cars and vans ranging in age from 0 to 12 years old and found that the median battery health across those was 95.15%. When we break it down by age, the numbers are still great. 4 to 5-year-old EVs have a median battery health of around 93.5%. 8 to 9-year-old EVs still retain about 85% of their original capacity. Even vehicles with over 100,000 miles on the clock typically hold on to around 90% of their original battery health. And by the way, the 2.3% annual degradation rate I mentioned from the 2025 Geotab study actually rose last year compared to 1.8% in the same report a year earlier. Why? Why the increase? The main contributor is probably that drivers are using ultra-fast DC charging more often. When the same dataset was limited to EVs that only use slow charging, the degradation rate was much slower at around 1.5% per year. Conversely, for drivers who use DC fast charging for a large chunk of their sessions, that rate increased to around 3% per year. Now, to continue on this tangent of what are the main factors that accelerate battery degradation, in addition to fast charging, the state of charge and depth of discharge matter a lot. Think of your battery like your stomach. It doesn't like being completely stuffed or completely empty. Consistently keeping the battery at 100% or running it all the way down to 0 puts a lot of chemical and mechanical stress on the cells. However, this often gets simplified to don't ever charge a battery to full, and that's not actually correct. Charging to 100% occasionally can actually help the battery management system recalibrate and balance the cells. Just don't charge it to 100% and then leave it sitting around like that for ages. Another common myth is that babying an EV with smooth, constant highway driving preserves the battery. But a recent study from Stanford University found the exact opposite. Their results showed that dynamic cycling, which includes stop-and-go traffic, regenerative braking, and even occasional hard acceleration, actually extends battery life by up to 38% compared to a steady discharge. They found that these dynamic driving patterns create tiny micro-rests that allow lithium ions to redistribute evenly, reducing localized mechanical stress and lithium plating. I personally tend to drive like a grandma, so perhaps this is a sign that I need to occasionally unleash my inner Oscar Piastri. Operating temperature is also important. Lithium-ion batteries tend to be happiest operating between 15 and 35 degrees Celsius. When a battery gets too hot, it speeds up internal chemical reactions that cause wear and tear, accelerating capacity loss. This is bad news for us Australians. In fact, simply leaving your car parked in the blistering sun with a 100% full battery is one of the toughest things that you can do to it. On the flip side, freezing temperatures slow down the flow of lithium ions, which can lead to a harmful buildup called lithium plating if you try to force a fast charge into a cold battery. And finally, battery chemistry matters. LFP batteries tend to tolerate full charge and repeated cycling better, while NMC batteries are more sensitive to heat and high states of charge, which can lead to faster degradation under certain conditions. One other useful thing to know about battery degradation is that it doesn't happen in a perfectly straight line, nor is it entirely unpredictable. It tends to follow a kind of S-curve like this, with a relatively sharp drop in capacity during the first year or two as the battery chemistry settles, followed by a long, slow, and predictable decline for many years. It only drops off steeply at the very end of the battery's true lifespan. The sharp initial drop in an EV battery's capacity typically occurs during the first 30,000 kilometers of driving and is mainly due to the formation of a solid electrolyte interface layer. When a new battery goes through its very first charging and discharging cycles, the liquid electrolyte reacts with the anode to create a protective film. This layer actually serves an important function, keeping the battery stable over the long term. But its initial formation permanently consumes a noticeable amount of the battery's usable lithium, converting it into degradation products. Fortunately, once the layer fully forms and stabilizes, this rapid capacity loss ends and the battery degradation slows down into a very gradual, predictable decline for the rest of its usable life. So this is all very reassuring at a population level. But what about these outliers that degraded much faster than the average? They may be rare, but they do exist, and like most secondhand EV buyers, I certainly want to make sure that I don't end up with one of them. I really don't want this video to come across as anti-EV or scare anyone off buying one. However, the fact is that repairing and/or replacing dodgy EV batteries is in some cases not as easy or as cheap as it should be. The EV Clinic, an independent European EV repair and research lab, has dug deep into manufacturer service catalogues and has publicly shared a spreadsheet that contains individual prices for all the drivetrain components for internal combustion, hybrid, and electric vehicles. Across the entire market, the EV Clinic found out that only about 2.5% of all electric vehicles have ever required a battery replacement, and for newer Gen 3 vehicles built from 2022 onwards, that failure rate drops to a microscopic 0.3%. However, worst-case scenarios absolutely do exist. When a battery does need to be replaced, the EV Clinic's dataset says the average price for a completely new battery is a little over 20,000 euros. But the range is huge, from a very reasonable 8,400 euros to replace the 58 kilowatt Tesla Model 3 battery, to the ridiculous 35,000 euros to replace the 62 kilowatt hour 2019 model Kona EV battery. That car only cost 39,000 new, and they're going for about 17,000 euros now at 7 years old. So imagine you're about to spend 17,000 euros on a second-hand car, and if you are unlucky enough to buy a car with a dud battery, that will cost you twice as much to replace as what you just paid for the car. You'd be better off scrapping the car and selling the battery to a reuse or recycling facility. So second-hand EV buyers are going to want to check the battery's state of health. This value is reported in the car's computer, but in a post-Dieselgate world, are we really going to just take the manufacturer's word for it? There are fortunately better ways. When you're looking for a second-hand car, you end up dealing with a lot of documents. Car ads, inspection reports, specs, contracts, all that kind of thing, and keeping track of all that information across different devices can get a bit messy. This video is sponsored by UPDF, an all-in-one PDF editor, which has been really useful while I've been looking into second-hand EVs. UPDF works across Windows, Mac, iOS, and Android, so everything stays consistent wherever you're working. You can edit text, images, layouts, convert files into Word, Excel, or PowerPoint, and it keeps the formatting intact. It also has OCR, so scanned documents become fully editable. The AI features are probably the most useful. You can summarize documents, pull out key points, translate content, or even ask questions directly inside the PDF. The recently released version 2.5 has some newer tools like AI bookmarks, which turn a big document into a structured outline, and AI search that understands what you're looking for instead of just matching keywords. UPDF is around 1/5 of the price of Adobe, and one account works across 4 devices. If you want to try it out, there's a link in the description where you can download it for free, and there's also a $10 discount during the new version release. Now, back to how battery health is tested. In rigorous scientific studies, measuring state of health is a highly controlled process that bypasses the car's potentially biased battery management system to find out exactly how much energy the battery can still physically hold. In a laboratory setting, the most fundamental way to measure capacity is through a direct measurement technique known as Coulomb counting. Researchers place the battery cell in a temperature-controlled environment. They charge the cell fully and then completely discharge it. As it discharges, they measure the exact electric current flowing out over time and integrate that data to calculate the total usable capacity. The state of health is determined by taking that newly measured capacity and dividing it by the original battery capacity that it had when it was brand new, which, by the way, means that they need to know what the capacity of this specific battery was when it was brand new. Unfortunately, none of the sellers of the second-hand EVs that I was looking at had the foresight to do this baseline test when the car was new. And furthermore, I don't have access to a lab to count coulombs. But it is possible to measure state of health out on the road with a deep monitored discharge test. In this test, you first plug a specialized independent diagnostic data logger into the vehicle's OBD port, that's onboard diagnostics. Then you charge the car to a full 100% and then drive it normally until the battery drains down to at least 10%. This deep discharge is critical because it forces the battery to show its true capacity. During this entire drive, the diagnostic box isn't just looking at the dashboard guess at battery capacity, it's continuously collecting hundreds of thousands of raw data points like current, voltage, cell temperatures, tracking exactly how much energy is being extracted in real time. That raw data is transmitted to an external server where it's analysed. The algorithms apply compensation factors for the ambient temperature and the discharge rate and spit out a health score at the end. So that test is possible to do on a second-hand car, although you need a special test unit and it is pretty hard to get a test drive that is long enough to take you from 100% to 10% states of charge. Conveniently, for would-be used EV buyers, British startup ClearWatt have developed an app that can estimate state of health without needing a special unit, without trusting anything from the car's own system, and with a shorter test drive. I recently spoke with Cameron from ClearWatt, and I asked him how they measure battery health without relying on the car's own data. He told me that they look at the effects of degradation instead. As batteries wear out, you get less range, and you can't put as much energy back in when charging. So their system uses your phone and just the percentage of battery remaining from your car to track real-world driving, including things like speed, terrain, and temperature, and then they normalize all of that to estimate what the car should be capable of. By comparing that to when the car was new, they can infer the battery's health.
And so what we've developed is a combination of connected car technology plus mobile telematics to be able to measure the driving range of an EV by looking at a series of trips that have been recorded with our telematics and with connected car data. So we use the mobile phone to collect GPS data every second whilst someone's completing a drive. So that, and not only are we getting latitude and longitude there, we're also getting altitude. We combine that with LiDAR data in the UK, so like a full scan of the terrain in the UK, which is accurate to like the nearest centimetre. It's crazy accurate to understand what that car is then capable of in a typical scenario, which we define as sort of 70% urban driving and 30% motorway driving, and then seasonality-wise, spring/autumn conditions. And if you compare that figure now against when the car was brand new, you can use that drop in range as a proxy for battery health.
ClearWatt can also increase the accuracy by adding a second test that looks at charging data. I did the ClearWatt test after I had already bought my car. It doesn't need a full discharge to generate results, but you still need to use at least 10% of your vehicle's battery in one go. So for me, that was probably 50 kilometers or so, and just a little bit more than a standard test drive would allow. The app is not currently available in Australia, but the ClearWatt team set me up specially, and they generated a report after just one test drive, so I could get this video out on time. Normally, you need 3 drives to get sufficient confidence in the report. The result from the ClearWatt test was greater than 95% state of health and an A+ overall health grade. I did also do a stationary test. I took my car to Mark Hemmingson from Electric Vehicles Canberra, and he plugged into the OBD to run a battery health test in about a minute with no test drive required. This test gives a percentage that is not merely the state of health value that I can get from the car, but to be honest, I had trouble finding out exactly what it is looking at. My understanding is that it is checking detailed battery parameters like cell voltages and temperatures, and maybe also includes some historical data like charge and driving behavior where available. It then uses a data-driven model trained on previous test results to infer the battery's condition, converting that into a percentage and a ranking compared to other cars of a similar type and age. Mine was only a little below average, which Mark told me is actually really good for an Australian car. Apparently, most of the tests he does, like this 2016 Leaf with 70,000 kilometres on the odometer that he tested right before mine, they mostly show accelerated degradation compared to the global averages it compares to. Mark attributes this to the hotter climate here, like we learned earlier in this video. My result from the stationary test was 98.5% state of health, so in the same range as ClearWatt, and I have no way to tell if the extra precision in this result is warranted from the simplified test method. My car is 3 years old and has done 14,000 kilometres, so we wouldn't expect much degradation yet, but it is great to rule out that it's prematurely failing. And what I love about having done this test early in the car's life is that now I can test again every couple of years and see how the degradation is progressing. Okay, this video has become longer than I intended, so let's start to wrap it up. A few years ago, when EVs were quite a new concept, everyone was worried about batteries dying before the car's life was finished. The data we have today shows that this was unfounded. The vast majority of EV batteries last for freaking ages. The real problem here isn't actually battery degradation, it's uncertainty about battery degradation. If buyers can't trust the onboard state of health number and they don't know independent testing exists, every used EV becomes a gamble. Independent battery health measurement is the missing piece. Once you can trust that number, once you know the usable capacity, buying a second-hand EV becomes much less risky. Personally, I actually chose to sidestep the issue. I bought a car with 5 years of warranty left. Partly because I hadn't done all this research yet when I bought, and partly because these battery health tests still aren't standard. Car ads here usually aren't even showing onboard state of health values, let alone the sellers having procured trusted independent battery tests before they started advertising the car. Which they absolutely should be. This just has to be the way things go if we're going to have a proper second-hand market for EVs. I actually found out from Cameron that things are moving in that direction. After having a bit of a rant about my Kia showing 100% battery health, even though it's clearly not brand new and must have some degradation after 13,000 kilometres. He told me that's actually quite common. Some manufacturers effectively hide degradation behind buffers, so the car keeps reporting 100% for years. The good news is that this might not be allowed for much longer.
What's quite hard to decipher when the manufacturers are keeping buffers is you don't know exactly where along that degradation curve you are. Because ultimately there has been degradation, but they're keeping that concealed from you by anchoring that battery health value on the BMS to 100%. So it is problematic. There is supposed to be standardization coming in Europe next year. So there's something called Global Technical Regulation 22, which is basically a framework that's been agreed by all of the manufacturers in terms of how they will have to present battery health within the vehicle, providing some form of moderation and testing of the accuracy of those values against a particular test cycle. It's a bit like the WLTP cycle. They kind of discharge and charge the battery, and they see how much energy can be put in.
So things are moving in the right direction, but we are not quite there yet. So yes, smartphone batteries degrade quickly, but they're treated terribly. Cooling, constantly charged to 100%, sitting in hot conditions with very little protection. EVs are completely different. They actively manage temperature, control charging, use buffers, and keep the battery within safe limits. Same chemistry, but a very different system. The real issue isn't the batteries, it's the information. Buyers need a reliable, independent way to understand battery health, and that's starting to emerge, at least hopefully in Europe. The question is how long it takes the rest of the world to catch up. Thanks to the Engineering with Rosie Patreon team and YouTube members who support these kinds of deep dive videos, and they can chat on the exclusive Discord server with me about all things energy. We'd love to welcome you to the team. You can join us at this link. Thanks also to UPDF for sponsoring this video, and thanks to you for watching. I'll see you on the next video.